A very warm good afternoon to all of you. I'm Sakshi, welcoming you all on behalf of Solar Quarter and First View Group to our much awaited webinar on modeling fuel cells and electrolyzer systems with multiphysics software. I take the pleasure to thank our speaker for investing his precious time to join the event, and a very special mention, of course, to our partner Comsol for their immense support to help organize this event. I would now request my team to play the commercial video.
Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL Multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL Multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL Multiphysics gives you the tools to build your own simulation apps. The Startup Wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via COMSOL Compiler, or by making them accessible by web browser via COMSOL Server. Understand, predict, innovate, and optimize your processes and designs with COMSOL Multiphysics.
Thank you so much, team, for playing that video. In recent years, a renewed interest has emerged in hydrogen fuel cells and water electrolyzer technology, largely driven by continuously lowered costs for intermittent renewable electricity generation via wind and solar technology. Modeling and simulation play a crucial role in the design and development of these electrochemical systems. Our webinar today with Console Multiphysics simulation software will help engineers accurately model, understand, and design fuel cells and electrolyzer systems in a time and cost effective manner. May I now introduce Dr. Rustam Shekhar, who is the technical specialist at Comsol, to give the presentation for his company. Over to you, Dr. Rustam.
Yeah, thanks, Ruchi. Now, I think we can launch the first poll question, which tells us the audience that what kind of audience we're talking about. So can you please launch the first poll question to us?
Sure. The polls are open throughout the webinar.
Okay.
The audience is requested to vote for the first poll. I will just screen it once.
Yeah, sure. Thanks.
The polls are open throughout the webinar. The audience can vote as in when.
Okay, so I think this poll will give us the fair idea that what pace that we should go, because the people who are new to console or new to simulation tool, accordingly we can try to explain and help them to the modeling of fuel cells and electrolyzer systems. So that's a very important data that we require when we talk to people with the different areas or different type of expertise that we are talking about. So I think we can now close the poll and we can start the session for today. So now we'll in this today's session, what we'll do, we'll try to talk about the console as we saw in the commercials. where we really talk about the what COMSOL multiphysics means, and then later we can go about the how we can handle the fuel cells in the COMSOL multiphysics. So when we start with the presentation with the introduction of multiphysics, so when we say multiphysics, it's a phenomena where two or more physical phenomena comes together, and then they will try to mimic the real world performance. So in a study, when you talk about any physical phenomena, let's say a simple water heater. So in water heater, if you see fundamentally, it's a wire which is conducting the electrons, and because of that, it may generate some kind of heat. So then we can only solve for the current flow and heat generation because of that. But the heat may dissipate by the conduction, convection, and in some cases radiations as well, because when we see red hot wire, then you may incorporate the heat transfer to it. So that makes the problem in multiphasic in nature, and you may be interested to see how that heat will flow into the liquid, and then because of that, what kind of recirculation we may want to design. So even a simple water heater also involves a multiphysics. So then you may require multiple physics to represent that phenomena. So what we can do with that, we can make a smarter design where you can take decisions on the designs, you can generate new ideas and reduce the cost. So cost reduction can be done because when now you're exactly replicating the physical phenomena, and you don't need to go for the multiple prototyping for your product, and you can reduce the number of experiments and speed up the product development. So that's what multiphysics may help you in the picture. So when you go for any kind of studies, we may see that system as a single physics, which can be the fundamental studies. In fundamental studies, you will pick one physics, you study around it, and try to know how particular things is functioning. So the workflow will be the same as multiphysics, but here you are only trying to get the one kind of physics that you want to add. Now you add the all relevant physics or chemical phenomena around the that particular system, and you couple them by using one coupling, which is a multiphysics, which represents the relation between those two physics. So as we talked about the given example of previous like a water heater, so you are solving for the Ohm's law, where you are trying to see the current flow in a wire, and then you are solving for the heat transfer, where you are solving for the Fourier's law. So in these two physics, heat sources will get transferred to the heat transfer, and those temperature distributions again can get affected can affect the electrical and thermal conductivity of that wire. So that way they will become coupled to each other, and you will get the multiphysics problem in nature. So this is how we can work on a single physics problem or the multi-phase problem. So single physics problem will give you the fundamental understanding of that particular phenomena, and then you add the different other physics, and you will get the multi-physics kind of scenario in that kind of in that system. So when we particularly talk about the fuel cells and electrolyzers, so fuel cells and electrolyzers are basically are the setup where you see the basic electrochemistry, which converts the one molecule to the other molecule, and then those molecules will be the charge species. So you'll see the charge transfer happening. So you will see the electrochemical reactions, and along with that, you will see the mass transport. If you working at a low temperature fuel cells or electrolyzers, so then you will be seeing the two different phases like liquid and gas, both are working together. So that way you will count the multiple physics that are working together, and then we will couple the all physics in a single platform. That will give you the complete picture of fuel cells, and you can add the other physics to complete the scenario. So in that case, we can go in the different ways, like you can compile the different physics and come up with a module, and or else you can start with a module which will represent your fuel cells, and then you can add the structural heat transfer and the electrical currents for the bus bar simulations. So that way you can start with a single cell level model, and you can extend up to a pack level model or a stack level model, including fluid flow, thermal management, and the connecting it to the other circuits like preprocessors or the post-processors or the fuels, where we have the fuel reformers, and at the last, if you are working at the electrolyzer mode, then you want to get a pure fuel. So that way you will have a central assembly, and then there can be supporting or the auxiliary assembly that you want to see around that particular setup. So with this, we can just share some success story which where console has been used, and they worked on that particularly on the fuel cells. So we can quote them as a success stories. So one of the success story that we can share it with you is from the NCL. So NCL is a government lab in India, which established in Pune. They work on fundamental research. So they was trying to address the one research problem where they want to get the maximize the performance, but at the same time they don't want to compromise on the other effectiveness or the other properties. So if we talk about, let's say, we will if will if we want to get the more current, then the one obvious thing is that we can extend the surface area, but extending surface area we may lead to the pressure loss or into the fuel cells or the electrolyzers. So that may give you more current, but then you may have the more losses in that particular physical phenomena or the setup. So there can be and many trade-off when we go for extending one particular property, but then other may get affected. So for the solutions for that, they perform the simulations where they primarily perform the impedance plots and the time dependent response for those particular setups. So they tested the different shapes, different layout, different materials, and the gas inputs. So they change the different properties and try to get the maximum power output from the setup. So the yield that you got was the maximum power out and the performance. For that, they use the electrochemical impedance spectroscopy, as we talked about. So you can see some of the results where we have a detailed cell has been modeled, including flow field, bipolar plates, and the stacking of it. And then they got the different stoichiometric and saw the current generated because of that. So this is the current profile that we get, and then we have a stoichiometry from 1 to 5. They have changed and saw the performance for that. So this is the one fundamental study which is done by one government lab. Similarly, if you talk about the one of the commercial person, which is Toyota. So Toyota wanted to design the flow field for their flow of their fuel cells to get the optimized fuel supply for their fuel cell system. So what they did, they got motivated by the bio available design where they wanted to replicate or mimic the fluid reactant distribution structures inspired by the leaves or lungs or the blood vessels. So with these designs, they come up with the different flow fields and tested them into the fuel cells for the optimum performance. So they did a fuel cell design in the North American Research Center of the Toyota Research Center, and come up with a optimum kind of a flow field for their fuel cells, which is inspired by the different kind of naturally available flow systems. And they deploy that fuel cells into the hydrogen fuel cells into cars, trucks, and even the cities for the stationary applications. So this is how console can be used in commercially and the government sector for the fundamental research to application level research. So so these are some success story which we wanted to share with you from our side. So now I think we can launch the one more poll question which we have, so that may give us the idea that if a person wants to work on a fuel cell, so what kind of applications they are targeting with that fuel cells. So because if you target different fuel cells, you will have the different kind of flow arrangement, different kind of structures that you want to work with, and you can get the different performance. If you take an example of like a mobile application or the automotive applications, there you may have a certain power demand, so then the structures and the flow field will be different. If you want to work on a stationary applications, that means power demand will be fixed, but you want to have a higher power output from that cells. And if you want to work with the power grids, that means you have the fuel cell system as an auxiliary kind of assembly, where in daytime if you couple it with solar panel, so then you can work with solar cells and You can store the energy by using electrolyzers, and at the night time same kind of fuel cells can be used for the power generation. So there can be different applications, or else let's say if some people wants to use for other applications, then they can mention that thing into the chat box, so then we can take up those different applications, and if possible we can showcase you the demo for that particular area. So please register the responses for this particular poll, and then after this poll, we will be going to the main presentation where we'll tell you if you want to model a fuel cells starting from the cell level model to a stack level model, how you can approach that particular problem. So please register the responses to this poll, and after this poll, we'll go for the detailed presentation for our fuel cells modeling systems. Okay, so I think that poll will be open in background throughout the presentation. So now you can just go to the presentation and see if you want to handle one fuel cells modeling problem, how that can be approached in COMSOL. So now, in summary, you can see there is a electrochemical setup is available here, where we can model our fuel cells and electrolyzers by using the interface available with fuel cell and electrolyzer, which will give you the ready-made interfaces to design the fuel cells, and you can perform steady state or time dependent or the impedance plots from the fuel cells. That includes the general electrochemistry, which will be primary, secondary, or tertiary current distribution. So primarily, when you talk about fuel cells, they will be based on the tertiary current distribution, which is Nernst-Planck equation, and the Maxwell-Stefan equations for the gas flow. And you combine it with different physics, and you can get the specialized functionality for that, which is gas diffusion layer, porous electrode, solid electrode, and the surface electrode. So these general electrochemistry will be coupled with the mass transport, and then later you can add the fluid flow, heat transfer, which can be single phase, multi phase, and then it can be in a porous media, free media, and heat transfer will be available in all three mediums. So when we talk about heat transfer you can see due to the conduction, advection, and the radiation in some cases where you have the surface to ambient, where you want to cool down the fuel cells in cases where you have the higher temperatures. So give to provide the properties or the functional properties to all three physics, which we can see right on the screen, which is electrochemistry, fluid flow, and heat transfer. You may require the thermodynamic properties, which can be from the gas side or the electrolyte side. So those different properties, if you want to calculate, so then you can use the thermodynamic database, which is available in the console, and from there you can accurately predict the kinetics for your fuel cells and electrolyte systems. uh, Now, if we talk about what kind of fuel cells or the electrolyzers you can target, so that will be based on the membrane which is being used. So you can if you use the proton exchange membrane, so it can be PMFC or the phosphoric acid fuel cell or the direct methanol fuel cell. So in all three fuel cells, you can see the proton exchange membrane, which is the Nafion in general. If you want to work on the membrane which is alkaline electrolyte based, so then you will see the alkaline membrane or the alkaline liquid, both can be used as an electrolyte. And similarly, for the higher temperature, we can see the molten carbon and the solid oxide fuel cells. In solid oxide, the oxide which is in available in solid format can be used as a electrolyte or the membrane. And so recently we saw the updates that people wants to bring down the temperature of SOFCs from 800 degrees Celsius to the lower temperature. So we may see the low temperature SOFCs as well. So they seems like low temperature, but they are not enough low to operate at room temperature. So but the developments are going on to operate them at room temperature or the fairly reasonable temperatures that we can work on. So it covers the all popular kind of membrane systems. And if you have a generic or the different membrane which you want to work on, so then you can add that membrane as well, and you can design your fuel cells or the electrolyzer. So this way, all popular fuel cells and electrolyzer system, and along with that, you will have the electrolyzer and fuel cells, which are unconventional that also you can model. So now, to cater that functionality, what we can do is we will have the same interfaces to design the fuel cells or the stacks level models. So we can start with very fundamental kind of model where we have three functional layers and flow channels around it, and we can obtain the fundamental understanding for my fuel cell operations. And later you can add the details like flow channels, you can add the details of cooling channels, you can add the details of other degradation mechanisms, and come up with a, detailed electrochemical models for the single cells. And those can be extended to the PAM kind of stack level models, and add the heat transfer to see the thermal management for that. So to host all those kind of properties, we will have the dedicated functional layers like gas diffusion electrode, porous electrode, and solid electrode. So these different kind of assemblies we will see when we go for the demonstration. So you can see the live console demonstration where we can start with a very fundamental or the very basic studies, and you can extend it to the stack level model. So we can show you in the software itself. In this fuel cell interfaces, you we can work with oxygen, water, or carbon dioxides, which can be carbon fuel. So this interface will be able to handle the carbon fuel as well. So if you want to work on direct methanol fuel cells, or CO2 electrolyzers, or the any other kind of fuel cells, so then you can work with that. Here you can see the bipolar plate and the electrodes both can host these kind of chemical species. So you can solve for the chemical species in the bipolar plate, where you can have the flow channels, and in electrode as well. At the low temperature fuel cells, you will see one very basic problem, which will be water transport in membrane. So then you can include that as well, and species crossover for the to see the losses of your active species, or else the voltage drop due to this crossover of oxygen and hydrogen. And built-in electrochemical and the chemical kinetics along with thermodynamics will be available. And to do the thermal management, you can see the heat generation by the joule heating, activation losses, and the concentration losses in the fuel cell systems. So now this will be your typical GUI where you can work on. So as you can see, the people who saw the console first time. So this is the console GUI where you can work on. So on top ribbon, this top ribbon window, or else in the model builder, you can see the all modeling steps which may be requiring to design one kind of fuel cells. So here you can see we can start with defining the components. We can add the geometry. We can add materials which we can use. We add the physics, where you can see few in physics we have the hydrogen fuel cells, and then we can go for the matching study and the result section. Later, if you want to convert them into an application which can be run standalone without having console license, so then that developer or the app builder section also is available. So now what we can see the all modeling step available here, and the physics responsible for the applications. So we have the hydrogen fuel cells where you can define the H2 gas diffusion electrode, or H2 gas flow channels, and the membrane. So now you can have the all five functional layers, and some additional physics, let's say free and porous media flow for the both sides, and the coupling of the fundamental study like fuel cells, and the flow studies which will be coupled by using these reacting flow techniques. So and then you can we can easily switch from fuel cells to electrolyzer by having this drop down. So it will be very easy to use interface where you can work on a fuel cells and electrolyzer system by having the dedicated functionalities and features for your studies. Now, how to formulate one simple PEM fuel cell problem, unit cell problem. So initially, we will take account of material transport, where we will do the material balance, which can be multi-component system, and you can see the hydrogen and air channels. We'll divide, or we can specify the hydrogen channels and the air channels. In hydrogen channels, we will have the hydrogen flow, which will be basically your negative electrode. In negative electrode, which will have the reduction potential zero, and other side you have air channels. So it's based on the composition, you may see the reduction potential for this side as well. To solve for the mass transport, we are solving for Stephen, which is a multi-component mass transport in channels and the porous medium. When we go for the porous medium, you will try to connect or correct this kind of setup for the effective properties due to the porosity. So we'll correct those effective properties as well. So once you do the mass balance, then we can do the charge balance as well. In charge balance, there will be hydrogen ion in the electrolyte. Electrons will be in the in the bipolar plate or in the electrode and the current collectors. And charge transfer reactions happening at the surface, which is governed by the Buttle-Bulmer. So flow of ions and a flow of electrons and the charge transfer of those species at the surfaces. So we can specify inlet, outlet, and the source and sink term for the ions or the electrons. So when you do the mass balance and the charge balance, then you can work towards the flow of the fuels, so that that flow will be in laminar region or in turbulent region in the free and porous media. So both air and hydrogen channels, you can design the flow, and you can design the flow for the cooling channels as well, which we can see in this particular image, where you have the channels for the air inlet and channels for the air cooling systems or the liquid cooling systems. Because we want to maintain the temperature of our fuel cells below 80 degrees Celsius, which is the low temperature fuel cell operating temperature. Due to the overpotentials, that this cell may get heat up, and you may see the membrane can get dry, that may lead to the degradation. So we always want to keep the temperature at a particular range, so that will give you the optimum performance. So the flow arrangement of the coolant along with the heat transfer, you will be able to maintain the temperature at an optimum range for your fuel cells and electrolyzer systems. So how that will be look like in a console interface. So this interface we saw earlier as well. So in we can see the full electrochemistry has been modeled. We can see the full flow and heat transfer has been modeled, and then the coupling between two also has been modeled by using the multiphysics node. Okay, so here we can see those kind of details for that setup. And now we can see the temperature profiles for the solid region, gas phase, and the water coolant and the heat sources. So this way we can safely map the those kind of thermal profiling along with the electrochemical profiling. So now this is the complete study about a single cell, where we can see where we need to work on the material side, where we have the relatively high temperature and high current densities for current collectors, that will give you the higher losses and local heat generation due to the Joule heating. And this particular simulation tells that poor conductivity of membrane will give you the higher losses. So that way we can relate one physics to the other physics, and try to work on the various aspects of the fuel cells or the electrolyzers to get the optimal performance and the simulations for that. Now, when we want to extend those studies for the stack level model, so interface will not change. We'll use similar kind of interfaces, and that interface again will be having the various details. So we just need to select those domains, and we can work on those kind of setups. So we have the coupled charge transport, chemical species transport, electrochemical reaction, heat transfer, and fluid flow. In this stack level model, uh, we will have take the full thermodynamic support for the reaction kinetics, water transport in gas and the liquid medium, composition, temperature, will give you the newer properties for the like transport properties, mobility, density, viscosity, and more. So either properties are getting affected by the operating conditions or the outputs, or else your property may affect your output and the operating condition. Both way this particular setup can be done, and you can design the bipolar plates, as we saw one of the story that Toyota use console to design the bipolar plate to design the flow field setup in the So now, if you want to see the other fuel cell setup, let's say we want to work on high temperature fuel cells, that is the SOFC. Here also the same interfaces has been used, two different interface like for the flow channels and the free media channels we added and coupled them by using the reacting flow. So it can be a high temperature unit cell, which is SOFC, or the stack level for the SOFCs. You can use it for let's say in some cases you may you may be not interested into the electrochemical performance, only the flow profiling for PAM fuel cells, because in PAM fuel cells flow is more important with compared to the electrochemical setup, because there you are dealing with a multi-phase system, and then that is available in free and porous media. So you are dealing with a system where you want to maintain the temperature, you want to operate at a two different phases like liquid and gas, and that too into free and porous media. So that will give you a very complex flow system. So then you may be interested to solve for those kind of flow systems. So you can add the two phase flow and obtain the oxygen bubble formation. That may also one of the degradation mechanism that can be possible in fuel cells, and oxygen evolution at the electrode surface. So those kind of flow arrangements, if you want to check for the flow fields for a cell level model or the stack level models, that again you can model. So recently, people have the interest in the alkaline water electrolyzers, because they're cheaper compared to the PAM fuel cells, and they are giving the better performance than the PAM fuel cells. So you can design your alkaline water electrolyzers along with the two-phase flow, and where we are using for the multi-phase, it's mixer model, and again full thermodynamics reactions or Volmar expressions, and the composition and temperature dependent transport properties has been given. And here we have solved the charge transport, chemical species transport, electrochemical reaction, fluid flow, and which is the fully coupled manner. So when we solve all these physics, so you will get the details and output related to those particular physics. As if you talk about charge transport, then you can see the current generation at local areas. You can see the mass distribution or the species distribution, and by solving chemical species transport, you can see the electrochemical reactions happening, which can be competing reactions at particular surface. So you will get the degradation. Degradation also can be modeled, which can take up some of the potentials. So you can see the enhance or potentials, and vice versa. You will get the more temperature rise due to those side reactions. Again, you can extend or you can work on the electrolyzers, which is high temperature electrolyzers, which is sort of like water electrolyzers, which follows the same technology which we saw in the electrolyzers, water electrolyzer in the low temperature, but then the operating conditions and the setup will be different. So in conclusion and a summary, you can see that you can work on the high temperature fuel cell, low temperature fuel cells, two phase flow, single phase flow, different kind of operating condition, different properties that you want to handle. So all will be coming into the single GUI, which is given here, and you can design your fuel cells at a very great detail. So now, if we talk about the which physics or contributes to the chemical species transport, so here we can see you can use the general purpose mass transfer interfaces, uh, which solves for diffusion, migration, and convection, and you can solve for the multi-component transport along with that is Maxwell-Stephen, and you can extend it for the porous medium flow. So we have two different approaches. One will be transport by dilute species and transport of concentrated species. In dilute species, we say there is no interaction between molecules, so the mass transport is not getting affected by the fellow molecules. So you can simply solve for Fick's law. But when species concentration is too high and the interaction of two molecules may affect the mass transport, then we can see the binary interaction of those gases and solve for Maxwell-Stephen. In some cases, when your pore diameter and porosity is less, then you can correct it for the Knudsen diffusion. For that, we will, and then we can have the mass sources coming from the Faraday's law that is being solved in the electrochemical setup. Okay, so if you want to work on fuel cells which are using the other species like ammonia, CO2, for that you can introduce one auxiliary species that can be used to trace the species or solve for the sulfur poisoning, or else any other species which is other than the available species like H2 and 2, CO2, CO, and CH4. So other than these five species, if you want to add one more species for tracer or for the seeing the operations other than the available species, so then you can add these auxiliary species and allow adding one more arbitrary species at both sides. So that means you can add two species and work on the different kind of fuel cells as well. So when you want to solve for flow, so it can be for single phase, which is Navier-Stokes equations, and for multi-phase, you will have the bubbly flow, mixture models, Euler, and phase transport, which follows the different criterias. But all kind of multi-phase systems, again, you can solve and you can couple it with the fuel cells to see the two-phase profile or the multi-phase profile of your flow field and the electrodes, which solve for which in general solve for the water management and the water transport in the fuel cells electrode and the channels. Again, you will extend those flow into the porous media, so then you can solve for Darcy loss, the Bringman equation, and phase transport, and then you can couple it with the mass transport by having the rejecting flow coupling between flow and mass transport. So, in summary, or the overall, you can use the fuel cell interfaces for electrochemistry, fluid flow to design single phase, multi phase flow, and then you can add the heat transfer to that setup. So we keep on talking about the properties, thermal properties. So what kind of properties that we are talking about? Here we can see the flow properties like density, energy for formations. So you can see the heat of reactions, formation, and the heat capacity, which are the thermal quantities. You can see the transport properties, which are viscosity, density, and the thermal conductivities, and the chemical properties like activity and the fugacity for So, for solving for these different properties, you can choose a model where you can have the different models for one properties. So, in this case, we want to solve for the gas viscosity that allows us to choose a model like Broco or Wilke and other kind of models. It will have the gas and liquid mixture properties and the equilibrium calculations. So where you will it will minimize the data or the entries required to do that kind of modeling in the fuel cells and electrolyzers. So if I will just list what kind of properties are required before prior going for the simulation, so you just need to know what are the porosities, what are the eccentric densities for your particular electrode that you have chosen, and that is a good enough data for any kind of for this particular fuel cell simulations in COMSOL. So we added the thermodynamic property, and in some cases you may require the material information. So for all popular fuel cells, we have the database for the membrane. So in aqueous alkali, you have potassium hydroxide, sodium hydroxide, and for molten carbonate, you have a lithium potassium carbonate and lithium sodium carbonate. For PMFC, you have a Nephion, which is liquid equilibrated or the vapor equilibrated. And for SOPC, you have a YZ, which is the 8 YZ setup. So we can use these different properties, and you can directly start using for Nephion, electrosmotic water drag, water absorption, gas permeation, and humidity dependent conductivity, which is the most popular membrane which is available in fuel cell. Now, when you have those kind of physics setup and functionality available, so what kind of test you can perform in console? So the primary thing which everybody wants to get this IV curve. So for IV curve, you can perform the stationary study. In stationary study, you can do the sweep or over a potential or current, and measure the other quantity. So if you want to sweep for current, then you measure voltage. If you want to go for sweep of voltage, then you can measure current. So that way you can have a plot and curve between IV between current and voltage, and yeah, there you can compare two different kind of setups. When we say do different setups, that means let's say you change one flow field and then you want to see because of flow field how my pollution curve is getting affected. So then you can do the study for both flow fields and compare the performance for your fuel cells. Similar thing can be done for the impedance plot. So you can introduce one of those harmonic perturbation and plot those Nyquist plots and compare two different kind of fuel cells. So we can perform the stationary study, or is the time dependent study, which can be current interruption. So let's say I want to test my fuel cells when current will get interrupted. What will be the transient performance of the fuel cell? So then you can see the current interruption. You can have a potentiostatic mode, dynamic loads, impedance spectroscopy, and in some cases you want to estimate the parameters for your fuel cells. So the parameter estimations for fuel cells also can be done in the console. So I think this is all from the presentation side. So now we can go for a small demo to see the modeling of electrolyzers or the fuel cells in console. So in conclusion, you will model the wide range of functionalities, and modeling units will be unit cells, stacks, electrolyzers, and electrochemical cells in general. So it covers the other electrochemical cells also, which can be flow batteries, and in some extent, if you want to use the same interfaces or same kind of uh, physics for battery applications as well. So now we can just switch to the console demo. So before switching to console demo, I can just show you the available product that we have. So today we talked about the console multiphysics, and along with that, into the chemical section, you will see the fuel cells and electrolysis module, which can be attached to the this base package, and you can perform your all fuel cells operations. And along with that, if you want to work on the CFD side, heat transfer side, structural mechanics sides of the prime fuel cells, and electromagnetic side of fuel cells, so then you can perform that simulations. You want to perform the optimization for your fuel cells, and interface or the link it with the other tools like CAD tools and the MATLAB Simulink. So, so by having the different functionality and coupling it with by using a single platform called COMSOL Multiphysics, will give you a detailed picture about fuel cells and electrolyzers. So, okay, so now this one small announcement from our side, that we are having a console conference at November 30 to December 1, where you can meet the console engineers, console developers, and the fellow console users, where the people who are using console, how they're using console, how they're getting benefited. So it's open to all, where the console users and non-users both are invited, where you can just participate and see how console is functioning for being used for the different areas. And there can be some mini courses also. So if you want to learn the tool for your research, and then you can learn that particular uh, applications as well in the console conference. So this is one small announcement from our side, which is about the console conference happening in Bangalore from November 30th to the December 1. Okay, so now with this, we can go to the console interface to see the GUI and how it will look like. So this is the console GUI when we open console first time. So you can follow the model wizard. So let's say I want to go for a model wizard. So it will ask you what space dimension you want to work on. So I can just choose the 3D models, and then now I can choose the physics that I want to work on. So I will go to the electrochemistry, and I can see I have the hydrogen fuel cells. So I can choose the membrane which I want to work on. And there's one generic interface also, which can be used for the any other kind of membrane which you want to work on. So, and then similarly, it is available for the water electrolyzer. So I will just choose the photon membrane. I will add this, and then I can choose the study type that I want to have. So I can have the stationary, time dependent, impedance plots, and cyclic voltammetry also can be added to this kind of study. So I can have the stationary study. So you will reach to a console GUI where you can do the all setup. So now here it is asking for the geometry for to model this kind of cell. So we'll just add the geometry, which can be imported or made in this GUI itself. So I will just insert one sequence which is available with us. Okay, so that is saved in console application library. So we have the fuel cell database with us, and I can just choose one of the geometry, let's say fuel cell cathode. I will just build all. So I will get the geometry which I want to work on. And now here you can just add the material. So I'll right click and say add material from library. So you can see the material available for that. So I'll just add the PEM fuel cell. So Nephon I'm adding. Okay, so now we have the some default nodes. So I can add the functional layers like membrane. I can add the S2 gas diffusion electrode. I can add the O2 gas diffusion electrode. And now I can assign those domains. So membrane is the central part, O2 is at bottom, sorry, O2 as at the bottom, and then H2 at the top part. So now I have assigned the membrane, H2 electrode and O2 electrode, where you can now software will automatically detect that electrolyte is available in all three phases. Electronic phase is being solved only in top and bottom layer, and then you can have the H2 gas phase and the O2 gas phase. With this, you can just specify at what mode you want to operate. So I will just make electric ground at the top, which is my negative electrode or the H2 electrode. I can add the operating conditions like potential at the bottom electrode. So now my cell is ready to simulate, and then I can get the results out of it. So now I have to mesh or create the discretization for my simulation. So I will just go to mesh and say build all. So that will give me a very good mesh to solve for the setup, and I can perform the stationary study to it. So to get the population curve, I will just add the parametric sweep, and here I can specify the potential and sweep for that potential. So this is one basic setup which you can have and compare two different kind of fuel cells. So now to just to see how those fuel cells will function. For that, we can just open one of the example model, which is the similar, which is a similar one, solid example model, to see what kind of profiles that we will get out of this simulation. So let's say I want to analyze this fuel cell. Okay, so now when we solve for the similar setup by using similar interface, I can obtain the pollution curve, which is the comparison of when we have the limited O2 gas phase and unlimited O2 gas interface. So when we add one more limitation, then you can see the pollution curve is dropping down, and we have the higher over potential for the similar current. You can track the species in the regions. You can track the pressures. You can see the over potential in cathode. You can see the local current densities. So all those details numbers you'll get once you solve for this setup. So this is one simple cell level model which you can see and compare at two different operating conditions. Now let's say you have a very detailed model including flow field. So you can have this serpentine flow field, and you can analyze the IV curve and as well as the flow fields for those kind of single cells. So previously there was no flow field available. Now we have added one more details to it, which is flow field to it, and we can get the same pollution curves. We can get the flow profiles. We can get the electrochemical profile for like electrolyte potential, and we can see the crossover of current densities and the water flux along the membrane. So these crossovers also now is the part of the simulation. One more extension of those kind of fuel cells can be done, and then you can go for a stack level model. In stack level model, we can do the cooling of the stack. So here we have the five different cells that you can model and see the results for that. So this is the stack with the five cells, and the thermal, electrochemical, and the electrical profile of that stack has been modeled. Okay, so here you can see we have the detailed stack where different functional layers are available, And the interface wise we didn't change, it will be the same, called hydrogen fuel cell. And but the when it comes to the membrane, we have assigned the membrane to the suitable domain. Again, when you see the S2 gas diffusion electrode, O2 gas diffusion electrode, so we have the complete assembly. So it's not any kind of simplification. The same level of details are available, but we are going into the detailing of those kind of stack level modeling. For the flow, we are solving Darcy law, and for the heat transfer, again we solving heat transfer into the entire setup. So this way, you can solve for this and again obtain the same profiling like polation curves and the temperature, phase profile, and the electrolyte potentials. So all those details again you can plot and you can visualize for that. You can perform the stationary or the time dependent studies in detail. So I think this is all from our side for the presentation and demonstration side. So now I think we can open the forum for the question and answers, and we'll try to address the questions from the audience side. So we'll take up some questions now.
Dr. Rustam, if you could just stop sharing your screen once.
Okay, so I think there is one question. Can I use my own microstructural design for GDL and MPL? So, if you have your own structures for GDL and MPL, so there can be two ways to address that query. First one will be you use the effective properties for that. Let's say in this particular fuel cell, if I'll go to the GDL, then I can specify the conductivity, volume fraction, and the permeability for that. So this is one way to do it, where you get the effective properties for your microstructures and deploy them. But in case you want to test your GDL or MPL in the real manner, and you want to use a real structures, let's say you got some SEM images, and those you want to test for your fuel cells. So yes, then you can work on a very detailed model where you can import those GDL or MPL structure. So I can show you one example where let's say in porous media flow, fluid flow. Uh, okay, so these kind of structures where real 3D structures you can import and deploy your physics, and you can test your GDL and MPL for those kind of modeling. So this is one random 3D structure for the fuel cell, and you can work on those kind of scenarios. So I think there are two different approaches which you can take on. One will be average property, another one will be the real structures that you want to work on. So I hope that answers your query. Okay, so in next question, that in which section we do PAFC simulation. So if you PFC, when you if you specify the alkaline kind of fuel cells, so if you want to ask about like what level of what level of detail that we can go, so we can start with electrode level models that can be extended to the stack level models for the even for the alkaline fuel cells. So and then so here it's so in the console GUI itself you can choose which interface you want to use, and then similar to the PEM fuel cell, you can work on the alkaline fuel cells as well. Okay, so I think if we can have the more questions, so we have sufficient time. So please post a question so we can answer them by giving the live demo of it.
Meanwhile, the audience is posting questions, so we can probably just publish the first poll that we have.
Yeah, so till the people posting the questions, we can launch the last poll question that we have, so which will help us to address you like what should we do after this session.
Dr. Rustam, would you like to add any closing remarks?
Yeah, so I think if there is no question, so I would like.
One more question we've got, just one second.
Yeah, okay, we'll take that question as well. So, can we import the material property or geometry from other commercial tools? So, yes, I think as we showed in our presentation in the last slide, where you can see that you can add the geometries, or you can import the geometries from other commercial platform like SolidWorks or the Pro-E and other things. And if there any material property, that also can be imported in form of new materials, and you can make your own material gallery where you store them, and you can work on those materials and compare them in different formats. So I hope that answers your query. So if you need more details, so then you can contact to us as well. So for if you want to ask any further queries, or else now or afterwards, so then you can directly contact us at the support at the console.com. So the email ID is support at the console.com, where you can ask queries about the console, and in general about the console applications for the various other application areas as well. So yeah, with this, I think we reach to the end of our presentation, where we try to answer the queries which we have in the during the session. And if you have other queries, then those we will be answering through the our support portal with a supporting document.
Dr. Rustam, I think these were the questions that we had. You may now give your closing remarks. Thank you so much, Dr.
Yeah.
Rustam, uh, for this incredible session that we had. A big thanks and shout out to our audience. With this, we have come to the end of our virtual event, and we would like to extend our heartfelt gratitude to the audience for investing their time and support for the event. Very special thanks to Comsol for being a facilitator here, and Dr. Rustam, you were incredible as a speaker, as co-host when the queries were answered. So we promise to bring back more such exciting sessions. The floor is now open for networking. Thank you, everyone.
Yeah. Thanks. Thanks everyone.